A large part of my day is spent in baffled astonishment that humanity has gone beyond this planet, that we have sent our robotic explorers to other worlds. We have gone to explore every planet in the solar system, dozens of asteroids. We've looked at comets. We have touched down. We've retrieved samples from other worlds. And this is a thing we do and can do. And it is just, again, when you sort of start to really wrap your mind around how much humanity has done so far and what the future holds, it is really impressive. We should be proud of ourselves. And yet we are living on borrowed time, that the conditions both of our planet, of our existence, of the sun will inevitably reach the end, and we will no longer be able to accomplish these incredible things. So it's a race against time for us to be able to explore the solar system, and hopefully eventually we will continue on and go on to explore the Milky Way and maybe the entire reachable universe. My guest today is Dr. Caleb Scharf, and he has written a new book that goes into an incredible amount of detail about this history of space exploration and puts it in the context of just where we are as a species, the amount of energy that's required for life to be able to accomplish these kinds of things. Now, Caleb Scharf is a very famous astrobiologist, author. He has contributed to many of the papers that I have reported on at Universe Today, many of the stories that we report on Space Bites. His work is instrumental in a lot of things we do. And so when I heard that he has a new book and his publisher asked if I wanted to interview Caleb, I jumped at the chance, read his book, and coordinated the interview. And so that's what this is a conversation with one of the people who I consider to be one of the most influential people in the field of astrobiology and space exploration. We talk about the book and sort of some of the interesting stories and kind of amazing discoveries that have been made with our human and robotic explorers across the solar system, and then shift gears into what is really Caleb's main focus, and that is astrobiology, and specifically how we search for life within the solar system and how we will look for technologically advanced civilizations out there in the universe. And as we sort of reckon and deal with the strange gap between this expectation that life should be everywhere and that yet we don't see life anywhere, and how do we pull this together? So I think you're really going to enjoy this conversation with Dr. Caleb Scharf. Caleb, congratulations on writing another book? What is this, your 8th? How have you done?
I wish. It's my 5th, I think.
5th.
My 5th trade book, yeah.
Yeah. And this is interesting, and we're going to get into this later on in the episode, but I definitely want to start by talking about your book, because it is one of the most comprehensive histories of human space exploration and robotic space exploration of the solar system that I've read in years. And it was not the book that I was expecting to read. Even as I was sort of reading the first few chapters of it, I started to realize where this was going. What was sort of your intention in writing the book?
It's a great question. Part of my intention was to sort of open people's eyes up to what has been happening in space exploration over the last 60, 70 years, because I think even for me, it's easy to forget just how much has happened, how much has been done, the extent to which we've become an incredibly sophisticated species in terms of exploring beyond our planet. So partly I wanted to capture that story, but then as I was thinking about that, I realized that I also wanted to get to the big question of what does it mean when a species breaks free of its planetary origins? And obviously, we've thought about this for a long time, over hundreds of years, perhaps people have speculated on this, but what does it really mean? And I think we have a different perspective today than we did, say, 50 years ago or 100 years ago, to do with the nature of evolution, to do with the nature of our engagement with the machines that we produce and the technology that surrounds us. So, it all sounds very ambitious, but I wanted to try to capture both sort of the natural history of space exploration as an interesting story that I feel not so many people are fully aware of, but is really important to understand because it's part of our lives today. But also this big picture and this big question of what happens not just to the species that breaks free from its planet, but all the other life that goes along with it and that is affected by that species. So yeah, there were several things I wanted to tackle in the book.
And you sort of spend a big chunk of the first part of the book sort of marveling about this idea that a species can actually get itself off of the planet, and that, you know, along natural processes, the gravity well is a astonishing barrier that prevents any kind of access beyond, you know, crawling around, climbing under the surface of the earth. That there's something very special about what we are capable with our tools.
Absolutely, yeah. And, you know, some of this comes down to the quantitative details. If you look at sort of the energy that biology makes use of, and the level of energy that, you know, runs an individual organism like you or I, or even a whole species, it's kind of pitiful when it comes to the challenge of lifting yourself out of a gravity well in a planet. And, you know, you need to find ways to do that from the resources around you. And that's not doesn't seem to be a built-in part of most biology on the Earth. And so what's interesting about that is the key to unlocking space for a species actually comes from thought. At least that's my premise, which is that, you know, being able to lift ourselves off of the surface of the planet requires a capacity to engineer and re-engineer the environment around us, to extract things like, you know, combustible chemicals that can be made into a propulsive rocket. But the key behind all of that is thought. It's decoding the nature of gravity. It's decoding the nature of things like energy and momentum in order to figure out exactly how to do this, because you might be able to sort of randomly create something explosive and possibly throw something into space once, but to keep doing it, to do it predictably, to do it, you know, again and again in a precise way that places things where you want them to go, it takes an awful lot. So it's kind of a fascinating issue, I think, for not just for us, but thinking about life in general across the universe. You know, how often does this happen? The species figures out how to overcome this extraordinary energy barrier that is gravity, that's so very different than the energy levels that we see in biological organisms.
And as you move through the chapters, you talk about our exploration of the moon, the exploration of Mars, the outer solar system, and asteroids and so on. There's just kind of these two threads going on. One is saying, you know, here's what we learned, here's what we sent. And then part of you clearly is going, and I can't believe we did it. And this was so hard. And here's how things broke. How did they even figure this out? Do people not realize the dangers and the challenges of what this took? You know, like sort of hand in hand, I think there's a kind of astonishment that all of these accomplishments were actually made, and that it didn't go much worse.
Yeah, absolutely. Yeah, no, I mean, I've obviously been an enthusiast for space since I was a kid, really. And that's driven me in my career. And, you know, you kind of pick up bits and pieces of, wow, that happened on that mission, or this happened on that attempt to launch something. And you have these small anecdotes kicking around in your head, but it's not until you sit down and you really dissect different missions and the history of space exploration that you just realize the number of incredible things that we've overcome in individual missions and as a whole, the sort of circumstances where we've had to fix something, right, on the fly. You know, there are beautiful examples of this. And I try to balance my enthusiasm for just going on about these things in the book with, you know, having them serve some purpose, which, as you kind of alluded to, it's sort of illustrating what it really means to be space explorers. It's not just, you know, hit the on button and go from A to B. There's all this other rich stuff that takes place. And because of the extremes of space exploration in terms of the physics, in terms of the technology required, you can find yourself in some pretty bizarre situations. You know, there have been situations of The first U.S. probe to orbit the planet Mars arrived in the I think early 1970s and discovered the planet was shrouded by a dust storm, so it couldn't see anything. The orbiter couldn't see anything, and it had to literally be reprogrammed on the fly to last out for another 2 months before it could resume its science operation. So it's not just things going wrong, it's the unexpected of the natural world throws itself in your way. And we've seen this again and again. There have been fantastically interesting complications with things like the Cassini probe at Saturn, releasing the Huygens probe into Titan's atmosphere. And there were design flaws that were so esoteric that nobody had put their finger on them until things were happening. And then they had to redesign things like the trajectory of the spacecraft to adapt for problems with the frequency at which data was being transmitted and so on. So yeah, so there's, I could have doubled the size of the book by writing about all of these stories, but I wanted to pick a few of them that really got across that sense of wonder and excitement, and wow, we can do this stuff, and it's so fascinating, and we learn so much. It's one of the purest forms of exploration left to us, I think.
But I think we live in this really strange place where, like, on the one hand, I think most people, just your average person's knowledge about space exploration kind of stopped in the mid 1980s with Cosmos. Like, you'll talk to people and they're very familiar with the Viking experiments and the Voyager spacecraft, and they don't really know that much about New Horizons or what's happening with, Juno. And maybe it's just a mass media kind of thing. And then on the other hand, people's sort of idea, sort of their expectations of how complicated space exploration is informed by science fiction, which is not helpful. Star Trek, Star Wars, they're not. The Expanse maybe gives you a bit of a glimpse of what space exploration might feel like, and there's this gap. And that was what it felt like when I was reading your book. It was like, yes, somebody is showing that so much has happened, like just an unbelievable amount of discoveries have been made, and they were hard won against an unforgiving environment with grumpy technology. And yet here we are with so much new knowledge.
Absolutely. And I think, there's this incredibly rich story that for whatever reason, maybe we've just become too familiar with hearing, a space probe went there, or we got some new data, right? It pops up in the newspapers again and again. And as a species, we do seem to have a tendency to become a little bit numb to things that we think we've heard before, even if we haven't, because it has some familiarity. And then, sure, the science fiction. I mean, I love science fiction, right? But it does sometimes diminish the extraordinary nature of what actually happens out in space and what we can actually do. So I did really want to try to fill that gap between the era of Apollo, which I think even now people can be in awe of when they're reminded of it, and what's happening today. And, we've been to all the major planets of the solar system. We've been to minor planets. We've been to asteroids. We've studied the sun. We've flown closer to the sun than ever before at extraordinary speeds. We've also placed thousands of devices in orbit around our own planet, a network, a web of machines that monitor the planetary surface, that provide communications, that allow us to navigate across its surface with exquisite precision and accuracy. That's amazing. And I think people don't always get that perspective. And I think it's increasingly important for people to have that perspective, to make decisions in their own lives, but also to make decisions that impact others, whether you're a company executive making choices about how you operate. It's surprising how much space, machinery influences what you do and what you need.
And again, sort of leading off of that, we sort of live in this really strange sort of dichotomy, almost this sort of quantum entangled state where on the one hand, we've got a whole generation of people who are expecting a city on Mars any day now, that a billionaire is about to send rocket after rocket after rocket to Mars, carrying all of the bits and pieces of a city. And on the other hand, it seems possibly too complicated and expensive to return one small capsule from the surface of Mars that is containing a whole bunch of samples taken by the Perseverance rover. How do we close that gap so that we can sort of align our recognition of reality?
That's a great question. And I think obviously in the book, I don't fully answer that question. I think it's important to understand that, the cost of some of these things in modern real terms is actually not that great. Okay. We might feel like, several $billions is a huge amount of money. But of course, compared to the total budget of a country like the US or other nations, it's not so very much. Some of it, we're in an interesting time right now with this, as you say, greater attention to the idea of placing humans back on the moon and then onto Mars. And of course, Mars has, for whatever reason, taken on this aura of, we must go to Mars. And I think that probably goes back to, when people thought they were seeing canals on Mars and so on. It's kind of it's sort of imprinted itself in our collective consciousness as the other place. And in many respects, it is one of the more accessible worlds in our solar system, even though it is so alien compared to the Earth. I think we're at this interesting juncture where something like the sample return, picking up those vials of samples that the Perseverance rover has collected on surface Mars, bringing them back using a robotic system, is really difficult, right? There's no getting around that. It's super difficult. And part of the difficulty is that there isn't an infrastructure there to do it. So I think what's going to be really interesting is the push to take humans necessarily requires the construction of an infrastructure that we haven't seen before. And some of that may involve the moon as a sort of stepping off point and a technology test bed, but it may involve just building a whole bunch of things, certain billionaires' rockets and so on. If that infrastructure starts to be built, then suddenly lots of other things become much, much easier. And, is it reasonable to put humans on Mars scientifically? Yeah, I think so. I think you can do an immense amount of science, not just with humans on Mars, but with the infrastructure that you need to build to put humans on Mars. Bringing back samples becomes trivial. Well, a few 100 grams of Mars samples is what you put in your pocket as an astronaut and you bring back to show your grandkids, right? I mean, obviously you wouldn't do that because you're concerned about contamination and so on. So, yeah, we're kind of at this interesting point where even if one doesn't agree with the motivations of some people or agencies for getting people to Mars, if you did, it would change things dramatically. It would open up the science of the solar system. It would open up a scientific understanding of another planet that has ramifications for understanding of our own existence. There's no getting away from that. So yeah, we're at this kind of crazy, interesting moment in history. And I don't know which way it's exactly going to go. And obviously in the book, I talk a little bit about options for places like Mars. And I think there are different paths that we can take. And some will be more successful than others, probably.
But you do open the book with the ticking clock that, we all reference on a regular basis, this idea that the heat from the sun is steadily increasing, and within 500 million to 1.5 billion years, Earth is cooked. Our oceans will boil. The age of large animals on the surface of the planet will be over, and that there is this window where these elements have come together, that there is an intelligent species that is capable of thinking these thoughts and it actually sent hardware out into space. And it's kind of taken as a given that if we don't figure it out, who will?
Yeah.
What do you?
Yeah, no, so as you say, I start the book with, the simple statement, we are a dying species, right? And,
Yes.
and that is in part because down the line, we know that there are going to be inevitable changes to the Earth because of the aging sun getting more and more luminous. So there'll come a point where the Earth begins to dry out. Our water will get sort of disrupted in the stratosphere and we'll lose the hydrogen. We won't ever make those water molecules again. And then a little further down the line, in 4 billion years' time or so, the sun will undergo much more dramatic changes as it stops fusing hydrogen in its core in the way that it's doing it right now, and it will inflate, become a red giant, and bad things will happen to anything remaining on the Earth. But it's also the case that evolution means that no species is really static ever. I mean, there are certain species that have persisted in their current form for a long time, but that isn't forever. And, modern humans haven't been around for that long. Maybe a few 100,000 years, maybe a million or so. We're going to change into other things regardless. And so there's this interesting situation that an intelligent technological species finds itself in that really does make it ask, is there a way to prolong the state that we're in or the state that we're going to become? And so, one could be more forgiving of various billionaires who want to, save us from existential risk. But, exactly how you navigate that is a really fascinating question. But I do think we're at a point where, like it or not, we're going to be doing things that open up the option that we extend our existence or our lineage beyond the lifetime of the Earth. And that's pretty remarkable.
Mm-hmm, mm-hmm. Yeah, I always think about this idea that we have extracted many of the easily extractable materials. We've dug the oil, we've mined the metals, we've sort of skimmed the surface of the Earth for the good stuff, and we've used it to make our machines and to send our spacecraft into space. And that if we somehow mess this up, then we need to wait for the octopuses to evolve a level of intelligence to start making, thoughts about going to the moon. And then they go, oh, and the humans used all the oil and the humans used all the titanium, right? What have we got left to work with here? And that, I think, it's beyond just the amount of, our impact on the environment as it is today, but our impact kind of on the future of this whole process. If we don't do it, then it's going to take a long time before things replenish to the point that another species can take a proper crack at it.
Yeah, I think that's a really great point. And, hydrocarbons, as you say, that's a limited resource, and we've sort of built our modern civilization on the back of that. And at some point, it'll be gone. We can replace the energy with other means. Solar energy is the obvious because there's more of that than we can possibly know what to do with. But yeah, down the line, it's an interesting. This question comes up in people's considerations or alternate histories as well. What if we were on a planet that never had great reserves of gas and oil? Would a species like us actually get to where it is now at all? Or would it have to wait for the octopus to come along and, be more inventive and creative than us and jump to nuclear fusion or something like that right away? But, the interesting thing about considering a future where some of our resources come from off-world is that it's on a scale that is completely unprecedented in the last 4 billion years of the history of life on Earth. The solar system is abundant with resources, whether it's metals, rare earths, hydrocarbons, water, carbon monoxide, you name it. It is out there. And I think that's part of this interesting projection that we can make about, how do we preserve ourselves as a species? And it may be that, you extend out into the solar system, but you also grow. You inevitably grow into something vastly larger than a single biosphere as we have on the Earth today. And that also means we spread out and we become diluted. And dilution is interesting in evolution. When you look at what has happened on the Earth, when species populate essentially new terrain, and thinking of someone like Darwin and his voyage on the Beagle, which I talk about in the book, The Galapagos Islands were populated with species that presumably originated elsewhere, but then you get this speciation happening. Each island, those species become something new again. And I think that's perhaps part of the future of us and of life on Earth, if it does indeed really make that jump to the rest of the solar system, is the level of resources means there'll be a lot more of us, or a lot more of the things that we become, perhaps not us as we are today.
Caleb, what are you obsessed with right now?
So I'm always obsessed with different things. So with my work, I'm really obsessed with machine learning. And I'm obsessed with machine learning as a approach to some of these fundamental questions about looking for life in the universe. So AI and machine learning. So I feel that this quest that we're on to understand the nature of life, to understand whether or not it exists elsewhere in the universe, is one of the most challenging and complex questions we've ever really come up against. I mean, yes, we've done quantum mechanics and, gravity and so on, but we know that life is really complicated and messy and unpredictable and so on. And the way it imprints itself in the world is complex and unpredictable and messy and difficult to decode. To me, the methods of machine learning and deep learning and AI that we have today are really the first time we've had a mechanism for handling data and complex phenomena that are sort of beyond what our minds can handle. And so I'm really obsessed with the notion that our best chance at finding evidence of life elsewhere, whether it's in samples on the surface of Mars, whether it's further afield, whether it's in radio signals that we're detecting, our best chance is that we construct machines that have that capacity to find these subtle, complicated, difficult to decode signatures of life. It seems like a perfect match to me that the most complex phenomena we know of in the universe, which is life, has to be tackled by the most complex tools we have at our disposal, which are currently machine learning tools, which are becoming more and more complex and more capable every day. So that's my current obsession. So I'm trying to, go back to my roots in coding and machine learning. Back when I used to be a cosmologist when I did my PhD, and I have a chapter in a thesis from the 1990s, a long time ago, where I actually tried to use a neural net to do cosmology. And it never got published because people didn't quite understand what it was doing, and I couldn't quite interpret the results. But in retrospect, I think that obsession has stayed with me, that we have these remarkable algorithmic tools. Let's put them to use on the most difficult questions we have in science.
And can you give me like a sense of how you sort of see this applying? Because, I think for most people, when they think about machine learning and think about artificial intelligence, they're thinking about large language models. But that's just one tiny subset of how you can use this technology to understand processes, to simulate things. How are you sort of seeking to approach this?
Yeah, so one approach is to, as you say, not worry about language, but worry about conventional data. So we have, for example, laboratory methods and actually instruments that fly on spacecraft that do things like mass spectrometry, so trying to decode the elemental abundances and molecular structures in a sample of stuff. Right. And there are other tools that we can bring to bear on that same question. We can shine a laser on material and then detect the spectrum of the light that's being re-emitted. And that tells us something about the molecules and the structures in a sample. So one of the things that we're trying to do, and I'm doing this with a wonderful team of people, we actually recently were awarded some funding to do this. These include people at the Carnegie Institute in Washington, D.C. and elsewhere. We're trying to gather very large data sets of these sorts of analysis data, so mass spectrometry, what's called Raman spectroscopy, which looks at the light emitted from compounds when you shine a laser or something on them. That data is messy, it's complicated. It takes a lot of training of humans to decode it and to say, oh, there's a molecule of this there, or there's a molecule of that there. We're trying to build a data set, a sort of foundational data set of thousands of samples that span the range from things that we know have life in them to things that don't have life in them. And without prejudicing the machine learning algorithm, we're trying to see if the machine learning systems can actually learn how to classify these samples on their own. That there is something different about this one than this one.
Yeah.
And it turns out that difference is life.
Right. And it might be that we didn't even recognize what those characteristics were. It's sort of like people who get really good at determining the gender of a chicken. They don't know how they do it, but they're able to do it. And you can sort of imagine.
AI, yeah.
Well, but even just this that you gain these skills, right? I'm like, this is one of the sort of the mysterious is that they hallucinate. We don't really know how they work and how they think, but it might very well be that they are predicting. They're detecting something in the way all of the different pieces are coming together.
Exactly.
That gives you an indication that there's life there in a way that you might look at it and go, I don't see it. Oh no, wait, there it is, right?
Yeah, no, exactly. And that's really the motivation here, is that, there may be, subtle non-linear correlations between different parameters, different variables that you can measure that a human won't necessarily spot. And if we don't have a prior theory of why there should be a relationship, we're not going to see it.
Yeah.
Right? We're just going to go after the things we know. And so so the exciting thing about this work, and we don't know what the outcome will be yet, is that these machine learning systems learn to do things differently than us, and they become really good sort of agnostic life detection systems, that they will spot aliens that we wouldn't see because we're making too many assumptions about what we expect to see.
Yeah, that's really interesting. It's very exciting. Hopefully, do you think this could be miniaturized and put onto a spacecraft so it can just start firing lasers and Raman spectrometers at various targets and see what it sees?
So these sorts of instruments already have been flown. So they exist on Mars at the moment. What we're hoping with this current work is to understand whether we can optimize the design of these instruments for feeding data to AI, for feeding data to machine learning, because those algorithms may need and want slightly different forms of data than we currently go after. So we're trying to close the loop. Essentially, can you build an astrobiologist that is an algorithm with its instruments, and the instruments are designed for that algorithm, and will it do a better job than we've done so far?
Yeah, that's really interesting. Caleb, thank you so much for taking the time to chat. Congratulations on completing the book, and good luck with all of your research. I can't wait to see this algorithm fly.
Well, thank you so much. It's really been a real pleasure to chat.
All right, take care. I hope you enjoyed that conversation with Dr. Caleb Scharf. We had a longer chat about his role of being this sort of new generation of researchers who were sort of given permission to start to think about humanity's search for technological civilizations, to look for smart aliens as opposed to the dumb aliens, and what it felt like to be on the inside of this search, and how this community has been growing over time, and sort of what they're currently thinking about and wrestling with. So we've got that conversation as a longer version of this interview over on Patreon. Of course, we call it Interview Plus. It will also be made available in the podcast completely for free. There's no ads. You can just go watch it right now with that additional content. Why are you even still here? Go watch that one over there. I'll put a link in the show notes so you can check that out. Now, I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Baylock, Cy Nielsen, David Veribath, David Gilson, David Matz, Evan Pro, Greg Feely, Hudson Ward, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Marcel Spitz, Michael Purcell, Modzo, OneStepForAnimals.org, Paul Robach, Ren Kaidu, Richard Williams, Sean Sargent, Stephen Fowler-Munley, Team 49, Telescopes Canada, Vlad Chiplin, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. I have to sort of admit that Caleb is like a big get for me, that, I have been admiring his work from afar for decades. A lot of papers. His name just keeps coming up. It's collaborations. A lot of the other people that I interview or talk with, Dr. David Kipping, Jason Wright, a lot of these people are sort of in the same area. Adam Frank. And they do a lot of collaborations together. Sometimes all of their names are on the same paper, and they are writing about the kinds of stuff that I am absolutely fascinated with. And, it really is great that there are people who both have this deep academic knowledge, who have been trained as cosmologists, who have this astrobiology experience. They're the principal investigator on, more conservative types of missions and experiments and things like that. And yet have this ability to think out of the box, to consider really clever ideas, to write about them in a way that is very accessible to the regular public and people like me, and that we can kind of interface and chat with them. And I think, that is the best in science communication, in my opinion. People who are doing the work, who are also communicating the work out to a wider audience and recognizing that enthusiasm that exists out there in the minds of the public. That's what Carl Sagan did so well. And that's what people like Neil deGrasse Tyson are doing today. And, I think Caleb and others of that sort of group are continuing on that work. So I hope you enjoyed the conversation, and we'll see you next time.